Welcome to an instructional series on AC systems. Around the world, the vast majority of electrical energy systems generate and transmit power in the form of three-phase alternating current, or AC for short. In this first section, we're going to be looking at why specifically alternating current has been selected for this purpose. There are two main forms of electrical power: alternating current and direct current. Alternating current takes the shape of a wave with varying voltage and current over time. Direct current, by contrast, takes the shape of a line with fixed voltage and current over time. Alternating current is the preferred standard in the power industry for generation, transmission, and distribution because it possesses a number of significant advantages over direct current. The first and most important among these is that alternating current enables the most efficient transformation from one voltage level to another. We need this capability in modern grids because these contain components functioning at a host of different voltages that need to be connected. For example, generators running at 20 kilovolts, transmission lines running at 500 kilovolts, distribution lines running at 20 kilovolts, and households running at 400 volts. These all operate across a range of voltages, meaning that vast amounts of power must be regularly stepped up and down, requiring optimal transformers to minimize power loss. AC transformers are preferable to their DC counterparts as the alternating flux allows for simple architectures that are highly robust and have minimal power loss over expensive and wasteful power switches. Let's now talk about how we can visualize these AC signals. There are two main ways to represent normal operating voltage and current waveforms as sinusoidal signals. The first is a cosine equation linking the three parameters of peak amplitude, frequency, and phase angle. The second is what's called a phasor. This makes use of complex numbers to encode the same information. These are special and require us to make a very key assumption that the system is in sinusoidal steady state. What this means is that these three parameters are unchanging, that is, time invariant, meaning that our xt is stationary. Phasors can be derived by rewriting the equation using Euler's formula. As we are only interested in the real part of the signal, we can ignore this right half. As you can see, we've taken the exact same three parameters of amplitude, phase, and frequency and reformed them into a different equation, of which we only take the real part. The complex coefficient there at the start is the phasor, and it neatly contains the peak amplitude and phase angle disconnected from the time-varying part. A phasor defines the time-invariant information of the time-varying sinusoids. This makes sense because we've removed reference to the time. So instead of picturing a voltage or current waveform like this, with the phase angle increasing off to the right, we can instead picture it like this, about a unit circle, with the phase angle representing how far the signal is around. This makes sense because after 360 degrees, the signal repeats itself, as it would after one full revolution of the circle. Also, you can see that for a given angle, we have the exact same amplitude on both graphs. A good example is 90 degrees. I've shown you how to derive a formula. Let's now talk about the benefits of phasors provided in circuit analysis. Phasors can be used to simplify not just voltage and current waveforms, but allow for a better understanding of the impact of different circuit components on signals. The first case is resistors. Current can be expressed as a function of time and as a phasor. the equations are as follows. Note, this is identical to the previous notation. In order to get the voltage phasor for a resistor, we use Ohm's law, V equals IR. Now that we've secured our voltage and current phasor, we can plot in the complex domain. The current phasor of a resistor can be seen to be at some angle phi, while the voltage phasor of a resistor is simply this multiplied by some resistance scalar. The second case is inductors. The currents are the same as before, with time and phasor representations as follows. However, this time, to find the voltage across the inductor, we use the formula V equals L times di dt. This gives us the following. And knowing the following, and that multiplying by J is just an anti-clockwise rotation by 90 degrees, we find our phasor representation for the voltage. Using this phasor representation of the inductor, we can draw the diagram with the current phasor I being at some angle phi again, and the voltage phasor V being 90 degrees removed. Remember that the angle increases in an anti-clockwise direction. The third case is capacitors. Starting with the voltage now, we know the voltage across a capacitor as a function of time and as a phasor. Now working to find the current, we use the formula I is equal to C multiplied by dV dt. Again, here we see a multiplication by e to the j90, which results in an anti-clockwise shift of 90 degrees. Knowing then the phasor representation of the capacitor for both voltage and current, they can now both be expressed diagrammatically. First, the voltage, this time at some angle phi, followed by the current, 90 degrees removed. Note that this is the exact reverse orientation to the inductor. Before we continue, we need to get a concept very clear, and that's RMS values of voltage and current signals. RMS stands for root mean squared. Cast your mind back to our discussion about AC versus DC, and you would remember we noted some differences in the waveforms. When it comes to power, we want to be able to compare the effective power despite the difference in waveform, so something like a peak value doesn't help us much at all. Instead, we assign a voltage value based on the average power dissipation in a resistive load. For a sinusoid function, this means dividing the peak value by square root of 2. What this means is that a sinusoidal signal is generating the same amount of power in a resistive load as a DC signal of 70% the peak value. It's important to note that if you ever see a quoted voltage on equipment or an outlet that is AC, it will always be RMS values.